welcome to my submission for the Simulink Student Challenge. My name is Ifeanyi Chukwu Obidike, and this is the adaptive gait stability monitoring system that I worked on. So I'll be taking us through the slide. To introduce us to the project, and then from there I'll be taking us to the MATLAB and Simulink environment to simulate the model that I designed. So the safety challenge, real-time gait instability. The challenge in rehabilitation engineering is patient safety. Specifically, how do we monitor and predict gait instability in real time, especially for users of devices like the rollators. Now, the first point here is the critical safety risk. Gait instability is a major safety concern for lower body assisted medical devices. Very important. The second point is low latency requirement. The monitoring system must make reliable, high-frequency decisions to intervene or alert before a full fall occurs, which is also very, very vital. And the goal of the project is to develop a model-based design control logic that provides continuous, validated, and embedded ready stability assessment. So on the screen is the image of an old woman losing balance while walking with her rollator inside her house. So if you observe closely, you can see that she's losing balance, almost at the verge of falling. So this reiterates the goal of my project, which is the adaptive gait stability monitoring system. It monitors the stability of the patient in real time and sends feedback. It monitors the stability of the patient in real time and indicates if the patient is stable or unstable. So over here on the screen is the model-based design, the control logic architecture. So here, this is the Simulink environment, what the Simulink environment looks like, and this is the model. This is the front workspace block, Simulink block. It gets data from the MATLAB workspace, the input data from the MATLAB workspace with which it works with, and it displays this lamp over here, displays it indicates if the patient is stable or unstable. If the patient is stable, the block will indicate green. If the patient is unstable, the block will indicate red. And below, just below the block, is the display block as well. So if the patient is stable and the lamp displays green, this display block right under it will show 0. Then if the patient is unstable and the lamp indicates red, this display block will also display value of 1. So I'll be taking us now to the Simulink, to the MATLAB and Simulink environment to simulate the model that I designed. So quick one. So this is the MATLAB code that I wrote to extract the IMU input data from the data set that I used. So note that the sampling frequency is 100 Hertz, and then the sampling time is 0.01 seconds, which is 1 over the sampling frequency, f of s, fs. So we'll be loading the participants' data now. So data 8, and we'll run the model. We'll run the code. So here it displays successfully prepared 3,168 samples of data. So like I said, the sampling time is 0.01 seconds and the sampling frequency is 100 hertz. So we'll now head over to our Simulink model to simulate this data. So these are Simulink model that we're working with. Gait monitor model.x SLX. So this is the Simulink model. So this is a front workspace block that gets the data from the MATLAB workspace, data it works with, and then the data goes through series of filtration, derivation, through the zero crossing logic to get the swing phase trigger, the stance phase trigger, the adaptive stability output, and then the alert status. Finally, before the lamp displays if the patient is stable or unstable, and then the display block will also show the value of 0 or 1 as the case may be. So let's run the model and see. So this is what the lamp block is now showing, is now indicating green light, which is telling us that the patient is stable. So I'll be taking us through the scope plot to see the individual, the swing phase signal, the stance phase signal, the adaptive stability output, and then the alert status. So from the first, the swing phase signal scope plot. So this is it. Remember, we made use of zero crossing logic, and this is now above 0, which indicates that the leg, or should I say the foot, is above ground level, is at 1. So we'll now check the stance, which is the stability. It's used to monitor the stability actually. So we can see that the stance came back from 1 to 0, indicating stability. So we'll now check the adaptive stability output scope plot, still at 0, and then the alert status still at 0. So the patient is stable. The lamp indicating green and the display block indicating 0. So I'll be taking us back to the MATLAB interface to get the data of another participant, this time around participant 4. So here is the data we're working with for the second validation. Remember, this data is what I used to validate the model. So we are done with the stability, the data that shows that the participant is stable. This data is from participant 4, record 10. So we run the code, and you can see the samples of data is now changed, and it's now 2,439 samples of data. We'll head back to the Simulink model, and then we'll run the model. And now the lamp is indicating red, and the display block is now indicating the value of 1. So I'll be taking us through once again through the scope plot of the swing phase trigger, the stand space trigger, the adaptive stability output, and the alert status scope plot. Let's start from this one. So the swing phase signal is indicating it went from 1 to 0, which is, and then the stance phase signal went from 0 to 1, indicating instability. Now the adaptive stability output, this is adaptive stability output signal, and the alert status is now indicating, showing us that it's from 0 to 1, indicating instability once again, and the lamp is indicating red, and the display block is indicating the value of 1, showing that the participant is stable. So with these two data, I have now used it to validate the model and come to a conclusion that the first data indicates that the patient is stable, while the second data indicates that the patient is unstable. There are a couple of other data. If we go back to the MATLAB workspace, to the MATLAB environment, rather, there are a couple of other data sets that are here. Other participants, the data set contains data of 23 participants, mixed age and mixed gender. So I made use of participant 23 and participant 4. And participant 23 is a quick one. Participant 23 is a female, and participant 4 is a male. So there are other participants, different age, different gender, different weight, height, foot length, knee height, shoulder width, elbow span, and wrist span. Okay, so there are other participants here, but this model was validated with two data from the 4th participant and the 23rd participant. So back to the Simulink, to the MATLAB workspace. This is the live script code that I made use of, and this is the Simulink model. So yeah, I'll be taking us back to the slide. Okay, so to slide. In conclusion, the key achievements from this before the conclusion, I also generated the C++ code after simulating the model. And over here is the C++ code, the model, the source file, and the header file. So this is the source file, and this is the header file. So let's start with the source file. So the code generation objective is for execution, efficiency. This is the source file, and this is the header file. So this is the final step of this project. I utilized embedded coder with the ERT target to generate optimized production-ready C++ code directly from this from the validated Simulink model. And this is the generated header file, like I said. Notice the use of class encapsulation and the eliminated blocks listed in the file. So these are the eliminated blocks. These are the eliminated blocks. This proves that the code is highly optimized for execution efficiency, which is very crucial for microcontrollers and field programmable gate array deployment at the required sampling frequency of 100 Hz. So yes, this is the header file. So I'm taking us back to the slide in a minute. Taking us back to the slide. So in conclusion, the key achievement from this project is that I successfully developed and validated an adaptive gauge stability monitoring system entirely using Simulink. And the impact is that it provides a reliable, low latency solution ready for integration into assistive medical technology devices like the rollators. So the next step is I plan to full hardware in loop testing on a microcontroller running on real-time operating system RTOS. So in conclusion, the adaptive gauge stability monitoring system is a fully validated real-time control logic that moves the concept of gait monitoring from modeling into deployable, optimized, embedded code. Thank you for your time.